In the world of fighter jets, compromise is a death sentence. So how did an aircraft built on compromise become one of the most pragmatic and dangerous machines in the sky? This is the story of the JF-17 Thunder, a fighter defined not by a quest for perfection, but by its sheer, stubborn will to exist. The JF-17 did not spring fully formed from a designer's sketchpad. Its lineage is a tangled, multi-decade saga of adaptation, aspiration, and geopolitical whiplash. Its genetic blueprint can be traced back to the ubiquitous Soviet MiG-21, a design so successful and prolific that China's Chengdu Aircraft Corporation reverse-engineered it to create the Chengdu J-7. For decades, the Pakistan Air Force, PAF, operated these J-7s, along with a menagerie of other aging platforms. But by the 1980s, the need for a modern replacement was acute. This led to one of the more ambitious and ultimately ill-fated collaborations of the Cold War's twilight, Project Sabre II. The concept was audacious, a best-of-both-worlds fighter that would marry the rugged, proven J-7 airframe with the technological sophistication of the West. In 1987, the PAF commissioned the American aerospace giant Grumman to lead the effort, envisioning a radical transformation of the diminutive J-7. The plan was to surgically alter the aircraft's very anatomy, excising the classic nose-cone shock intake and replacing it with a solid radome capable of housing a modern radar, likely the formidable APG-66 from the F-16. This necessitated a complete redesign of the forward fuselage, with new bifurcated air intakes mounted on the sides under the cockpit, a feature directly inspired by Northrop's F-20 Tiger Shark. The heart of this new beast was to be a Western turbofan, either the General Electric F-404 or the Pratt & Whitney PW-1120, promising a dramatic leap in performance over the J-7's asthmatic Chinese turbojet. For a brief moment, it seemed Pakistan was on the verge of creating a unique, potent hybrid fighter. However, the project was a case of geopolitical gravity proving stronger than aerodynamic lift. Grumman's own feasibility studies concluded the program was financially perilous, but the true death blows came from Washington. First, the 1989 Tiananmen Square massacre led to sweeping U.S. sanctions against China, severing the technological pipeline and forcing Grumman's withdrawal. Then, the Pressler Amendment triggered a full military embargo against Pakistan over its clandestine nuclear program, a move that not only scuttled any hope for Sabre II, but also famously blocked the delivery of F-16s that Pakistan had already paid for. The dream of a Pakistani-American-Chinese fighter was dead. Yet, this failure was the necessary prelude to the JF-17's birth. The Sabre II project, while producing no hardware, had successfully created a viable concept. The core design changes, the side intakes and solid nose, were the ghost in the machine, a blueprint waiting for a new set of partners to resurrect it. The collapse of the Western option forced Pakistan to engage with China not as a mere airframe supplier, but as a full-fledged co-development partner, forging a deep strategic bond out of the ashes of a failed American venture. When the resultant aircraft, now christened JF-17, finally took to the skies in 2003, its physical form was a direct echo of those early Grumman studies, a study in pragmatic engineering. The airframe is a conventional semi-monocoque structure, a deliberate choice favoring industrial simplicity over cutting-edge performance. It is constructed primarily of aluminum alloys, with high-strength steel and titanium alloys judiciously applied only in critical high-stress areas. This stands in stark contrast to its regional contemporary, the Indian HAL Tejas, which boasts an airframe composed of over 45% advanced composite materials by weight. The JF-17's metallic construction is a conscious trade-off. It simplifies manufacturing, lowers production costs, and makes battle damage repair feasible for air forces without extensive composite fabrication facilities. The price for this pragmatism is a higher structural weight and a significantly larger radar cross-section. sacrifices made on the altar of affordability and maintainability. Its aerodynamic layout is a well-understood configuration, featuring a mid-mounted delta wing blended with leading-edge root extensions, lurks, to enhance maneuverability and generate vortex lift at high angles of attack. Early flight testing revealed some control issues, prompting a redesign and enlargement of the LEIX, an example of the iterative, problem-solving approach that characterized the development program. The conventional empennage consists of an all-moving tailplane, a single vertical stabilizer, and twin ventral fins for stability. The entire structure is designed for a service life of 4,000 flight hours, with the first major overhaul scheduled at the 1,200-hour mark, a respectable, if not exceptional, lifespan that again reflects its cost-conscious design philosophy. This physical shell, however, is merely the vessel for the systems that give the Thunder its lethality. And at its core lies a powerful but temperamental Russian heart. The aircraft is powered by a single Klimov RD-93 afterburning turbofan, a derivative of the RD-33 engine that powers the twin-engined MiG-29. The primary modification for its use in the single-engine JF-17 was the repositioning of the gearbox to the bottom of the engine casing. Generating approximately 19,000 pounds of thrust in full afterburner, the RD-93 gives the lightweight fighter a respectable thrust-to-weight ratio and a top speed of around Mach 1.6. However, the engine is a product of a different design era and comes with a number of well-documented quirks. Most famously, at certain throttle settings, it has a tendency to emit a trail of thick, black smoke, an unsolicited visual signature enhancement that is less than ideal for a combat aircraft attempting to maintain a low profile. This has led to some design changes, such as widening the air intakes on later prototypes to improve airflow. Furthermore, the reliance on a Russian engine for a flagship Sino-Pakistani project has created its own geopolitical complexities, with past supply negotiations reportedly snagged by Moscow's concerns that the JF-17 could compete with its own MiG-29 on the export market. While China has been developing an indigenous replacement, the Guizhou WS-13 Taishan, Pakistan has shown a marked reluctance to adopt it, citing concerns over reliability and performance. This hesitation is a telling indicator of the persistent challenges in Chinese jet engine technology and underscores the PAF's pragmatic preference for a proven, if imperfect, Russian power plant over a less mature domestic alternative. The true strength of the JF-17, however, lies not in its airframe or engine, but in its mind, a surprisingly modern and pilot-centric avionics suite and cockpit. The human-machine interface is the aircraft's unsung hero. The glass cockpit is built around three large, full-color multifunction displays, MFCDs, that dominate the instrument panel, complemented by a wide-angle holographic head-up display, HHUD, and a comprehensive hands-on throttle and stick, HOTAS control system. This design drastically reduces pilot workload by presenting critical flight, sensor, and weapons data in an intuitive, customizable format. The layout has been lauded by those who fly it. One PAF pilot went so far as to describe the Thunder's cockpit as superior in its ergonomic layout, even to the F-16 he had also flown. This focus on the pilot's cognitive load is a hallmark of modern Western design that has been successfully replicated and arguably improved upon. The aircraft's brain is a federated architecture managed by two mission computers running on a MIL STD 1553B databus. The primary sensor has evolved significantly through the aircraft's production blocks. The initial Block Y and 2 aircraft were equipped with the Chinese NRIET KLJ-7, a capable X-band pulse Doppler fire control radar with a reported uplook detection range exceeding 105 kilometers against a 5 square meter target, capable of tracking 10 targets and engaging 2 simultaneously. The major generational leap came with the Block 3, which introduced the KLJ-7A Active Electronically Scanned Array, AESA, radar. This solid-state radar provides vastly superior performance, including faster scanning, multi-target tracking, higher resolution for ground mapping, and greater resistance to electronic jamming. However, this advanced capability comes with a critical caveat. Reports suggest that the KLJ-7A's effective detection range is insufficient to independently guide the aircraft's longest-range missile, the PL-15, to its maximum kinematic envelope. This creates a crucial dependency on off-board sensors, primarily the PAF's Sabre II Erie Airborne Early Warning and Control (AWACS) aircraft, which can detect targets at much greater distances and feed targeting data to the JF-17 via data link. This networked approach is modern but introduces vulnerabilities. The data link can be jammed, and the limited number of high-value AWACS aircraft become priority targets for any adversary. The offensive systems are backed by a comprehensive electronic warfare suite, typically including a radar warning receiver, RWR, a missile approach warning system, MAWs, and an externally carried self-protection jammer pod, all integrated with a chaff and flare dispenser. This combination of a conventional, relatively short-lived airframe and a legacy engine with a highly modern avionics core gives rise to a brittle but lethal tactical philosophy. A glass cannon built not necessarily to survive a protracted, high-G turning dogfight, but to leverage its advanced sensors and networked capabilities to achieve the first shot and the first kill from a distance. The lethality of the JF-17 is ultimately defined by its teeth, a versatile and surprisingly diverse arsenal that transforms the lightweight airframe into a genuine multi-role threat. The key to this flexibility is the integration of a MIL STD-1760 data bus architecture, a digital interface that allows for a plug-and-play approach to weapons integration. This design choice was strategically brilliant, as it prevents vendor lock-in and allows the aircraft to employ a wide spectrum of ordnance from Chinese, Pakistani, U.S., and even Turkish sources. With 8 external hardpoints, 1 on each wingtip, 4 under the wings, 1 under the fuselage, and a chin station for targeting pods, the aircraft can carry over 3,400 kilograms of external stores. For air-to-air combat, the JF-17 employs a layered defense. For close-in engagements, its primary weapon is the Chinese PL-50I, a capable infrared homing missile. The cornerstone of its beyond visual range, BVR capability, is the SD-10, the export designation for the PL-12, an active radar homing missile comparable to early models of the American AMRAAM. The Block 3 variant, however, introduces a game-changing weapon in the form of the PL-15E, a very long-range missile with a reported range exceeding 200 kilometers, giving the Thunder a reach that outstrips many of its regional competitors. In the air-to-surface role, its versatility truly shines. It can deliver a full suite of unguided iron bombs from the American Mk-82, Mk-83, and Mk-84 series, as well as precision-guided munitions. This includes U.S.-made GBU-10, GBU-12, and GBU-16 Paveway laser-guided bombs, often designated by a Turkish Azalpod targeting pod. It also deploys a family of Chinese GPS-INS guided glide bombs, such as the LS-6 and GB-6, which provide a significant standoff strike capability. For the suppression of enemy air defenses (SEAD) mission, it can be armed with the LD-10 anti-radiation missile. Its maritime strike capability is equally robust, centered on the venerable C-802AK subsonic sea-skimming anti-ship missile and, more alarmingly for naval planners, the CM-400AKG, a fearsome air-launched anti-ship ballistic missile that travels at supersonic speeds in its terminal phase, making it exceptionally difficult to intercept. Yet, for the Pakistan Air Force, the aircraft's most vital function is strategic. The JF-17 is a designated delivery platform for the Hatf-Veit Ra'ad, an indigenously developed air-launched cruise missile with nuclear capability. This role elevates the JF-17 from a mere tactical asset to a cornerstone of Pakistan's nuclear triad, providing a credible, survivable, and flexible airborne deterrent. This strategic importance is the ultimate justification for the program, ensuring its continued funding, development, and central place in the PF's order of battle. This bring-your-own-bomb philosophy, enabled by its open architecture data bus, is also one of its most compelling export features, allowing customer nations to integrate the aircraft into their existing logistical chains without being forced to purchase an entirely new, proprietary ecosystem of Chinese munitions, thereby drastically lowering the barrier to entry and total lifecycle cost. The journey of the JF-17 from a conceptual blueprint to a mature 4.5 generation fighter is a case study in the success of spiral or iterative development. Rather than pursuing a perfect, all-encompassing design from the outset, a path fraught with delays and cost overruns, the Sino-Pakistani team prioritized getting a functional aircraft into the hands of pilots as quickly as possible, allowing real-world operational feedback to drive a continuous cycle of improvement. The initial production batch, designated Block 1 and entering service from 2007, established the baseline platform. These were capable, if rudimentary, multi-role fighters equipped with the core airframe, the RD-93 engine, and the KLJ-7 pulse Doppler radar. They provided the PAF with a modern fly-by-wire aircraft and allowed the service to begin developing tactics, training syllabi, and maintenance procedures. This hands-on experience directly informed the next iteration, the Block 2, which rolled out from 2013. This variant represented the mature workhorse of the fleet, incorporating a host of practical upgrades. The most visible of these was the addition of a fixed in-flight refueling probe, significantly extending the aircraft's range and endurance. Block 2 also featured improved avionics, more robust data links, an enhanced electronic warfare suite, and a refined flight control system, making it a more effective and reliable platform across the board. A significant evolution came in 2017 with the introduction of the JF-17B, a two-seat variant. While its primary role is to serve as an operational conversion and advanced trainer, the JF-17B is far more than a simple school bus. It is a fully combat-capable aircraft, and the addition of a second crew member, a Weapon Systems Officer, WSO, makes it a potential force multiplier. In the increasingly complex battle space, the cognitive load of managing an advanced radar, multiple data links, targeting pods, and electronic warfare systems can be overwhelming for a single pilot. The JF-17B allows this workload to be distributed, making it an arguably superior platform for demanding missions such as complex air-to-ground strikes, CAD, or even acting as a mini AWACS by using its powerful sensors to direct its single-seat brethren. Design-wise, the JF-17B is distinguished by a tandem cockpit, a larger dorsal spine to accommodate avionics displaced by the second seat, and the novel addition of fuel carriage within its vertical stabilizer. The culmination of this iterative process is the JF-17 Block 3, which began serial production in late 2020. This variant represents a true generational leap, elevating the aircraft firmly into the 4.5 generation category. The upgrades are comprehensive. The pulse Doppler radar is replaced by the KLJ-7A ASA radar. A new wide-angle holographic HUD and a helmet-mounted display, JART Sight, HMDS, are integrated into the cockpit. A stealthy chin-mounted infrared search and track, IRST system, provides a passive means of detecting and tracking targets. The hybrid flight control system is replaced with a full 3-axis digital fly-by-wire system for improved handling, and the aircraft is powered by a more powerful and reliable RD-93MA engine variant. This philosophy of field now, perfect later, stands in stark contrast to the troubled development of its primary regional rival, the HAL Tejas, which suffered from years of delays, often attributed to constantly shifting requirements from the Indian Air Force. By getting a good enough aircraft into service early, Pakistan built a foundation of operational experience that ensured the subsequent, more advanced blocks were practical, effective, and tailored to the real-world needs of its pilots. In the final analysis, an aircraft's worth is measured not on the factory floor, but in the unforgiving arena of real-world operations. The JF-17's service record is a complex tapestry of combat successes, troubling export failures, and nuanced comparisons with its peers. With the Pakistan Air Force, its primary operator, the Thunder has been thoroughly blooded. Its combat debut came in counterinsurgency operations in the rugged terrain of South Waziristan, where it was used to evaluate and deploy a range of munitions against militant targets. Its most high-profile test, however, came during the February 2019 skirmish with India. In the aftermath of an Indian airstrike on Balakot, PAF JF-17's were tasked with retaliatory strikes on Indian ground targets, employing standoff precision-guided bombs. In the ensuing aerial melee, the PAF officially credited a JF-17 with the downing of an Indian Air Force MiG-21 Bison. Pilot anecdotes from the PAF paint a picture of a reliable, effective, and surprisingly easy-to-fly aircraft, with its digitized cockpit and resilient avionics drawing particular praise. The global ambitions for the JF-17, however, have yielded a mixed and cautionary tale. The program has seen notable successes, particularly with nations seeking to modernize their air forces on a budget and without the political strings often attached to Western hardware. Nigeria acquired an initial batch of 3 JF-17's, which have been effectively employed in counterinsurgency roles, backed by a robust training and support package from the PAF. The most significant export victory to date is the landmark deal with Azerbaijan, which has placed an order for up to 40 of the advanced Block 3 variants to replace its aging fleet of MiG-29s. This deal represents the largest export contract in Pakistan's history and a major vote of confidence in the platform's latest iteration. This success is sharply contrasted by the widely reported debacle in Myanmar. The Myanmar Air Force became the first export customer in 2018, acquiring 16 aircraft. However, the fleet was soon reportedly grounded due to a litany of severe technical problems, including allegations of structural cracks in the airframe, unreliable avionics, and persistent engine issues. The episode led to significant diplomatic friction between Naypyidaw, Islamabad, and Beijing, and served as a stark lesson. The JF-17 is not a simple fire-and-forget product. Its operational reliability appears to be inextricably linked to the depth and quality of the after-sales support ecosystem provided by the PAF, an ecosystem that was seemingly absent in the Myanmar deal, which was reportedly handled more directly by China. When measured against its key competitors, the JF-17's unique philosophy of compromise becomes clear. Against the HAL Tejas, it is a battle of pragmatism versus technological ambition. Where the Tejas leverages advanced composites for a lighter, stealthier airframe, the JF-17 relies on conventional metalwork for ease of production. The result is that Pakistan has fielded over 150 Thunders, achieving operational maturity, while the Tejas program has struggled with production rates. Against the F-16, the perennial benchmark for lightweight fighters, the JF-17 concedes superiority in raw kinematics and thrust-to-weight ratio. However, a new-build JF-17 Block 3 offers a more modern cockpit, a superior AESA radar, and longer-range BVR missiles than the older F-16AB and MLU variants that form the backbone of many air forces, including a large portion of Pakistan's own. The comparison with the MiG-29 is perhaps most telling. Azerbaijan's decision to replace its fleet of twin-engine, high-performance MiG-29 interceptors with the single-engine, multi-role JF-17 suggests a broader trend in air power doctrine, where advanced sensors, network-centric capabilities, and multi-role flexibility are valued more highly than pure speed and agility. The JF-17 is rarely the top performer in any single metric, but its competitive advantage lies in the combination of its affordability, its immediate availability to nations excluded from Western markets, and the powerful political backing of China. It is winning its market niche not by being a better dogfighter, but by being a better geopolitical and economic solution. The CAC PAC's JF-17 Thunder is ultimately the physical manifestation of the 80% solution. It was engineered to deliver roughly 80% of the capability of a top-tier Western lightweight fighter for a fraction of the cost, a goal at which it has largely succeeded. It is not an F-35, nor was it ever intended to be. It is a workhorse designed to be mass-produced, strategically independent, and lethal enough to pose a credible threat to more sophisticated adversaries under the right circumstances. Its success should not be judged against the bleeding edge of aerospace technology, but against the aging fleets of third-generation Mirages, MiG-21s, and F-7s that it was built to replace. In that context, the Thunder is a qualified but undeniable success. It is a testament to pragmatic engineering, a validation of the spiral development model, and a powerful symbol of a strategic partnership forged from geopolitical necessity. For air forces on a budget, facing complex security challenges in an increasingly multipolar world, the JF-17 offers a compelling proposition: a modern, capable, and above all, attainable fighter jet. It is a pragmatist's sword for a complex world, a reminder that in the calculus of air power, sometimes the best is the enemy of the good enough.